My name is Quinn Vitelli Hawkins. I am Chip Shearer's PhD student here at the University of New Mexico, and I'm proud to welcome everybody to the Planetary Seminar Series, again hosted here at the University of New Mexico and part of our grand challenge. So for today, we have Aaron Bell. And so Aaron is an assistant research professor at the University of Colorado Boulder and a trained experimental petrologist with extensive experience studying terrestrial and planetary igneous systems. His research combines thermodynamic modeling of mineral fluid equilibria with experimental techniques to explore chemical processes, shaping planetary interiors and driving magmatic activity. So today's talk will highlight some of his recent work on Angrites and their unusual origins. And with that, Aaron, we turn it over to you.
Thanks, Quentin. So thanks to everyone for coming. I guess there's a live audience at UNM. I didn't realize that. I thought everyone was online. So that'll be kind of interesting. Anyway, so I guess before I start, I should thank a lot of my collaborators. So a lot of the work I'm going to talk about today has really been done over the last 5 years, but it certainly wasn't just me who did it. So I've had important contributions from my graduate student, Lydia Pinkham, who graduated about 2 years ago, I guess, with her master's from CU. Chip Shearer, of course, has been involved in this. Tony Irving, involved as well. He lent me the samples that I did all this work on. He's also provided some interesting insight and input. So, and then finally, I want to thank a couple of collaborators for their help on some of the geobarometric data that I'm going to present. So Laura Waters down at New Mexico Tech helped me write some of the code. And then Mark Yorso, of course, is the MELTS guru, who also helped me with some MELTS code that went into some of this research. And so with that, I'll go ahead and get started. So if you don't know anything about Angrites, that's fine. They're kind of unusual, and I'll talk a little bit about why we're even interested in them. But first, I'll give you a quick outline of the talk. So the first part of the talk, I'm going to spend a few minutes talking about Angrites, sort of from a broad perspective, as in what are they and why are we even interested in them. And then I want to talk a little bit about why they're so unusual, and then some of the hypotheses that have been proposed to explain the origin of these really unusual, this really unusual suite of meteorites. And then I want to present some data that I've collected that sort of sheds new light on these hypotheses and the viability of the existing hypotheses for Angrite petrogenesis. And then finally, I want to talk about some really new data, some new geobarometric work that we've done, or that I've done recently, to help put new constraints on the size of the Angrite parent body. So this is a notoriously slippery problem that I think we might have a good solution to finally. And then finally, I'll leave you with some conclusions and some future outlook about the future of work on Angrites. I think there's a lot still to be done, and so I'll share that with you as well. So anyway, you might be wondering, what are Angrites anyhow? So Angrites are an unusual suite of igneous achondrites. As of last year, I think the last time I checked was maybe a year ago, there were 46 classified specimens, so there's not very many Angrites, and that's out of over 70,000 plus known classified meteorites, so they're a very small sliver of samples from a lot of meteorites. So Angrites are unique in a couple of senses. They have really ancient ages. So some of the oldest igneous crystallization ages in the solar system come from Angrites. They crystallize within a couple million years of CAI condensation, so they're very, very old, older than Forvesta. So there's a range of ages. Some of these are for plutonic Angrites. These ages over here, the 4564, that's the oldest age for what we call volcanic Angrites. So there's just a couple of pictures of Angrites. So this is a newer Angrite find from Northwest Africa, Oud Nemus 001 from Algeria. So you can see that these actually look a little bit like basalts. You can see these green olivine phenocrysts in here and some fine-grained ground mass, and they also have these sort of round cavities that some people have interpreted as vesicles. And here's just a thin section in plain polarized light of a very famous Angrite called Dorbani. It's found in Argentina in 1979. So if you look at these things, these are plagioclase laths. They look like basalts you might find on Earth, but they're very unusual for a couple of reasons that I'll go over here shortly. So just a bit more about the Angrite parent body. So we think that the APB, so if I say the word APB or the abbreviation APB, it's because I'm lazy and don't like saying Angrite parent body all the time. So we think that the APB probably contained a small metallic core. So this is using some tungsten isotope data that indicates this, as well as some siderophile element modeling. And so one of the more interesting things about the Angrites, and we'll come back to this, is the current whereabouts of the parent body are unknown. We don't really have a good parent body candidate for the Angrites. There's been a few asteroids identified that may be potential fragments of what I think might have been a larger Angrite parrot body, but we really don't know its current whereabouts. And so this sort of adds to the mystery of these samples. And so just a bit about where we find them. So most of the Angrites in our collection actually come from Northwest Africa. So this is just a picture of a meteorite being found in Morocco. So these come from commercial dealers and Berbers, nomadic Berbers in the desert find these and then sell them to dealers. A few Angrites have actually come from Ansmet or Antarctica. And so this is a few of the more famous Angrites in the Antarctic collection. There's very few that actually have come from Antarctica, but that's mostly where we find them. So how do we identify Angrites? What makes them unique? Well, there's a couple of ways we identify them. So usually they're identified with oxygen isotopes, and so Angrites actually have a unique cap delta 17O signature. And so essentially they plot on the Angrite fractionation line in cap delta 17O versus delta 18O space. And so they plot on this line here. And so you notice that this is not very far displaced from the terrestrial fractionation line. It's kind of interesting observation. And so down here, these are eucrites. So eucrites have a much lower cap delta 17O signature. I plot down here. And so another way we identify these things is with what I call Papike plots after the late Jim Papike. He actually proposed this idea. Sometimes I call them the poor man's isotope plots. And so it turns out you can actually identify planetary parentage fairly well by plotting manganese versus iron measurements made by the electron microprobe for minerals like olivine and pyroxene. And so here's actually some data that I collected here at CU Boulder. So this is the iron or the manganese to iron ratio of olivine phenocrysts in this Angrite that I'm going to talk a lot about today, called Northwest Africa 12774. And so you can see they plot on this trend that actually falls in between the Earth and Moon. And so they have a similar manganese iron ratio to other inner solar system bodies, which is also interesting, and I'll talk more about this in a bit as well. So Chondrules plot up here, Mars is up here. So Angrites always plot on this unique line. So that's another way we identify them. Yeah, the poor man's isotopes. Let me see if I can figure out how to advance this. There we go. So Angrites, what makes them unique? So one of the most unique things about Angrites is their unusual mineral assemblages. And this is what I think attracts some people to study them in the first place. And so this is an X-ray map of the Angrite Sahara 99555. So this Angrite's been around for a while, probably since the mid-90s, I think it was found. And so this is an iron X-ray map, and this just shows you the phase assemblage present in what we call a group 2 Angrite or evolved composition Angrite. And so Angrites are characterized by sort of these really unusual phase assemblages. And so these phase assemblages on the surface don't look that unusual. Basically, Angrites consist of olivine, clinopyroxene, and plagioclase, but it's the compositions of these phases that actually makes them quite unusual. And so the olivine phenocrysts in this actually are quite calcic. So some of the olivine phenocrysts have almost a weight % calcium. So this is massive if you know anything about calcium and olivine. These are very, very unusual. The other unusual compositional element of Angrites is they have these titanium aluminum clinopyroxenes that are actually going to be important for the geobarometric story that I'm going to tell later. And so these are also unusual. So we call these colloquially, they're called fasciatic clinopyroxenes, kind of an old-fashioned term, but essentially they're titanium aluminum-rich pyroxenes that don't look like the garden variety pyroxenes that you'd find from Mars or Vesta or anywhere else. And another interesting aspect of the Angrites is they're volatile depleted. And by volatile depleted, I don't just mean things like carbon, nitrogen. I also mean alkalis. And so the plagioclase in Angrites isn't really even plagioclase, it's actually almost in-member anorthite. And so that makes Angrites very unusual. So they're the only meteorites that we know that have basically no sodium in them. And so, you know, one of the other interesting aspects of Angrites is in these in the ground mass of some Angrites, we actually get some very unusual olivine compositions. And so maybe you remember back to mineralogy, the pyroxene quadrilateral. So often we plot clinopyroxene or we plot pyroxene compositions in terms of 4 in-member components. Well, it turns out you can do something similar for olivines. And so there's actually some calcic in-members of olivines. And so we have actually kirstenitic olivine. So normally when you learn about olivine in mineralogy or petrology, we usually talk about forsterite phthalate solutions, but it turns out you can actually put some calcium in the M2 site of olivine, and you can even make an in-member calcic olivine called kirstenite. And it turns out this kirstenite is actually found in Angrites or subcalcic kirstenite. And so these are just the compositions of some olivines. from actually Sahara right here. So these are measured compositions from this meteorite. And so you can see that some of them plot in this very unusual compositional space. So this is not the sort of olivine you learn about in petrology or mineralogy. So they're very unusual for that sense, or for that reason as well. They also have a series of interesting minor phases that range from silicoapatite, which actually has a mineralogical name now, to this weird phase called runite, which is often found in alkaline magmas around the world. It's a strange sort of accessory phase. Plus sulfide, ovospinel. Sometimes they have some camosite in them. So they're very unusual overall. Let's see if I can advance the slide here. Okay, there. But what really makes Angrites stand out, I think, from other meteorite groups is their silica activities. And so maybe you learned about silica activity in petrology, maybe you didn't. I'll give you a quick crash course. And so silica activity is just the chemical potential of quartz in silicate melts. And so it turns out that Angrites actually have a really unique silica activity in comparison to all the other achondrites that we know of. And so here's just a plot of silica activity that I've calculated. And so these are actually the silica activities that I've calculated from some iron-rich group 2 Angrites like Sahara. And then these are from the silica activity of a couple of Angrites that are more primitive or magnesium-rich. And so the point of this diagram is to basically tell you that meteorites that belong, or S&C group meteorites, that's kind of an old-fashioned term, but Martian meteorites, Shergottites, Mare basalts from the moon, all of the HED suite meteorites, as well as Morbs and continental flood basalts from Earth, and almost all of the ungrouped achondrites that I've looked at. I actually did a search here and looked through some ungrouped achondrite mineralogy. They're all classified as orthopyroxene normative. And so in this diagram, typically these meteorites would actually plot in the shaded field. And so here I have a little picture of the meteorite Erg-Chech, which is an ungrouped achondrite that has orthopyroxene in it, that actually plots above this olivine OPX buffer line right here. But essentially my point is that all of the known igneous meteorites from the solar system, most of them, there could be a few things that I missed, or a few outliers in addition to Angrites, but basically all plot in this shaded field up here, whereas Angrites plot down here. And so Angrites have this unique characteristic in that they're critically silica O2, or critically silica undersaturated. That's how we describe these compositions from a petrologic point of view. And that's what makes them unique, and that's what makes them sort of interesting. And so there's a lot of questions about how exactly one can derive critically silica undersaturated melts from what is roughly chondritic feedstock, but we think like the primordial material that accretes and melts to form these differentiated bodies. And so just for example, I gave in addition to Angrites, there are some critically silica undersaturated magmas from Earth. So olivine melolites and nephlenites are these sort of exotic magma types that are related to carbonate metasomatism in the mantle, as well as metallurgical slags on Earth. So the only other place that I've ever seen kirstenite is actually in metallurgical slags from ferrous metallurgy. So if you look at the slag left behind, sometimes you see some calcic olivine. And this is a testament, essentially, the calcic nature of the olivine and the Angrites is a testament to their critically silica undersaturated nature. And so the Angrites really stand out. So I kind of called them the odd man out in this sense. And so I think this is sort of my initial fascination with Angrites, is why don't the Angrites look like meteorites from all of these other groups, all of the other achondrites that we know of, or meteorites from other terrestrial planets or telluric planets in the moon. Like they're all essentially either orthopyroxene normative, or they plot above this buffer curve right here. And so this poses a really big challenge for understanding Angrites. And so that's what I want to spend the first part of the talk talking about. And so essentially the question that sort of drove me into this field in the first place is, well, I mean, if these are so unusual, well, how in the world do we get these anyway? And so it turns out there's actually been a fair bit of work done on this. And so the basic story, if you don't know the basic story of how you get achondrites, it goes something like this. So essentially, what we think is roughly chondritic, whether they're chondrites like we know them or not, roughly chondritic precursor material or undifferentiated material accretes into small bodies that eventually get large enough to partially melt via the decay of aluminum-26. That's sometimes thought of as the heat engine that drives the differentiation and separation of core formation in these differentiated bodies. And so essentially, how do we take sort of primordial precursor material that we know of and assemble it to make something that looks like an Angrite? And so it turns out that there's a few ways that you can do this that have been proposed. And so these are the sort of existing thoughts on how one might be able to produce Angrites from what we think is chondritic precursor material. So the Old Testament, or sort of the old point of view on this, is what I like to call the oxidized partial melting hypothesis. So back in the early 90s, Amy Jurowitz had done a bunch of chondrite melting experiments down at JSC in Houston, and found that basically if you partially melt carbonaceous chondrites under high FO2s or high chemical potential of oxygen or oxidized conditions, you can actually make melts that somewhat look like D'Orbigny and Sahara, these group 2 Angrites that I was talking about. And so this is sort of an old view. And so this was an interesting idea, and it's actually still quite good. The only trouble is you can't really explain the more primitive Angrites like the ones I'm going to talk about today. So anything that's more magnesian than these, anything that we think is more primary or primitive and it has magnesium-rich olivine in it, this hypothesis really doesn't work for those. But it's an interesting idea, and maybe it still applies to group 2 Angrites. I don't totally know. And so I think this is sort of the stepchild of all the hypotheses. So there was actually an interesting proposal by Albert Jambon in 2005, who suggested that you could potentially make angritic magmas by carbonated partial melting of chondritic precursor material, roughly chondritic. And so the basic idea is, and he took the inspiration from Earth, so all of these weird critically silica undersaturated magma types I was talking about that were terrestrial, those, it turns out, actually are related to carbonated partial melting the mantle. So the way you get an olivine melolite or nephlenitic magmas on Earth is you actually melt periddotites that have carbonate stable in the source. And so Albert Jambon actually pointed out the geochemical affinity between melolitic-like melts from Earth or nephlenites. So nephlenites have sodium in them, so they're not perfect analog for Angrites. But he pointed out this geochemical affinity and suggested potentially you could make Angrites by melting or by partially melting a carbonated periodotite mantle in a parent body, and you could get these very unusual liquid compositions like that. And so after this was proposed, nothing's really ever been done. It's been sort of left alone. But it's interesting, and I think it's worthy of some deeper consideration. And so finally, this is what I call the high temperature condensate enrichment hypothesis, or the nebular hypothesis. And so this is a bit ad hoc and I think in some ways unsatisfying. And so it was actually proposed by John Longy in a new paper that sort of had revisited some of Longy's initial observations and conclusions. You can make Angrites by essentially partially melting a mixture of something that looks like an ordinary chondrite and high temperature condensates that sort of look CAI-like. So essentially, if you take chondrites that are enriched in refractory elements, not in the form of CAIs directly, but some early high temperature condensate, you can actually make Angrites like that. And so basically, each of these hypotheses, in essence, is proposing a way that you can take essentially Angrites from being orthopyroxene normative to olivine normative or nepheline normative magma types. And so the way you can do that in each one of these, so you can destabilize orthopyroxene on the liquidus of Angrites by oxidizing conditions. You can do it by adding carbonate. So carbonate actually makes olivine and nephlenitic melts by expanding the stability of orthopyroxene on the liquidus and the mantle. And so you get these really critically silica undersaturated rich partial melts. Or basically you can do it by an unusual bulk composition. So basically, you can mix some unusual things together and you can partially melt that and make Angrites. And so this is sort of where things have been left. There's really not a lot of good data to explore these hypotheses with, or the extent to which they're correct or not correct, or might be correct or not correct. And so this is sort of where we're at. And so this is where my interest got piqued, and I was sort of interested in coming up with ways to actually evaluate these existing models. And it turns out that each one of these existing models has deep implications for the oxidation state of Angrites. So they each of those 3 models that I just described, or those hypotheses, only work under very specific redox conditions. And so one way that you can go about critically evaluating or casting a critical eye on these hypotheses is to actually go and collect new magmatic redox data from primitive Angrites in particular, and you can see if the measured redox values from these Angrites are consistent with what one would expect if one of those hypotheses were correct. And so this is the basic idea behind a proposal I put in with Chip Shearer back in 2020. to do some of this work. And so the problem with this, and the reason no one's done it, is it's actually a hard problem, and it's a difficult problem to tackle. Otherwise, someone probably would have done it. And so I'm going to talk about some measurements of polyvalent chromium and olivine phenocrysts from some primitive Angrites that we've actually used as redox proxies to evaluate these hypotheses. And then I'm going to talk a little bit about a few phase equilibrium constraints from some of these unusual, from a couple of unusual Angrites themselves that actually can tell us something and give us some insight into the oxidation state under which these Angrites equilibrated, and therefore, by extension, the oxidation state of their source regions. And so this will help us shed some new light on which of these hypotheses might be correct, which are clearly incorrect, and so on. Anyway, so most of today I'm going to spend talking about two really unusual and unique Angrites that really don't look like a lot of the others in a couple of important ways. So I'm going to talk about two Angrites, Northwest Africa 12774 and Northwest Africa 7812. And so here is a backscattered electron image of the phase assemblage in NWA 12774. And so this is an iron K alpha X-ray map. And so one of the first things, if you've looked at any igneous rocks, one of the things that stands out about these is these are actually porphyritic Angrites. And so they have this sort of like coarse-grained phenocryst assemblage. So these olivines are on the scale of, 500 microns, maybe a couple of them are on the order of a millimeter, 250 to 500 microns. There's also some clinopyroxene phenocryst, and these clinopyroxene, olivine, and spinel phenocrysts in these two meteorites are set in this really fine-grained quenched ground mass. I call it spinifex-like. It's not spinifex in the sense that these sort of needles are olivine. These are actually anorthite needles, but it's clearly a rapidly quenched matrix. And so these are unique for their textures. And so anyway, the basic makeup of these, about 35 volume percent olivine, 5% of these little euhedroclinopyroxene phenocrysts, a little bit of spinel. You can see the spinels creeping in right here. And then they have a ground mass assemblage that's basically anorthite, some more ferroin clinopyroxene you can't really see very well here, plus olivospinel and silicoapatite. And so one of the interesting things about these meteorites that I think has been sort of a red herring, and sort of Angrites in general, it turns out, despite the fact that we think they're modestly reduced, that if you actually look at the ovospinel, and these are quite small, they're 10 microns in the ground mass. If you look at those ovospinels, they're actually ferric iron-bearing ovospinels. They have about a 15 to 20% magnetite component. So this is kind of interesting for meteorites. You have a magnetite-bearing ovospinel in these unusual sort of Angrites that we generally think of as to be modestly reduced, but it even is more unusual in the case of these meteorites in that some of the olivines actually have big camosite inclusions in them, these camosite droplets, which I'm going to talk about a bit later. And so there's this kind of interesting juxtaposition of what looks to be an oxidized ground mass with a phenocryst phase assemblage that has spherical inclusions of metal. So this is very odd and sort of is a head scratcher. And so some of my interest in this is sort of unraveling this problem as well. And so one way to tackle this problem is to actually use polyvalent chromium and olivine as a redox proxy. So a number of years back, actually, when I was a postdoc and then a research scientist at UNM, I had actually proposed this and done some work on developing what I called a polyvalent chromium and olivine redox barometer. And so it turns out that typically most people think of as iron being the primary polyvalent cation present in silicate liquids, but it turns out there's other important polyvalent cations in silicate liquids. They're minor in abundance compared to iron, but they're present nonetheless, and these can actually serve as an important way to measure the oxidation state or an important redox proxy for understanding the oxidation state of silicate melts that are fairly reduced. And so it turns out chromium is a good redox proxy. And so in particular, it turns out that the chromium 2 plus to chromium 3 plus ratio of a given silicate liquid is actually transmitted undistorted into olivine fairly readily. So basically, the partitioning of divalent and trivalent chromium from a parental liquid into an olivine phenocryst is about equal. So essentially, the trivalent to divalent to trivalent chromium ratio in a parental liquid for an olivine phenocryst is basically identical to that of the phenocryst. And so this sort of gave me the idea that essentially olivine phenocryst, over the growth of olivine phenocryst, you can actually track redox evolution by virtue of measuring di and trivalent chromium ratios in olivine. And so it's actually long been known that the ratio of divalent to total chromium in silicate liquids is a strong function of oxidation state. And so in this plot, this basically shows, this is actually some old experimental data from the early 90s. They didn't do any fancy measurements of chromium valence. They actually inferred chromium valence ratios in silicate liquids from spinel solubilities, which was a very clever way to do this. And so the basic idea here is that really reducing conditions, and these are done on terrestrial basalts. This is some work by Roeder. So if you're familiar with the olivine KD value, this was actually determined by this guy Roeder. So he later did a lot of work on spinels as well. Anyway, so in this work, basically this plot shows the chromium 2+ to total chromium ratio of a silicate liquid as a function of FO2, and you can see that all of these spinel solubility measurements actually imply that chromium valence actually changes from essentially liquids with 100% divalent chromium, so essentially liquids with all divalent chromium, no trivalent chromium, all the way down here over about 10 orders of magnitude in FO2 space to liquids that basically have only trivalent chromium. And so the basic idea behind all of this is that if you can make these measurements of chromium valence and olivine, you can actually translate these into oxidation states, provided you have some experimental data to back that up. And so that's the basic idea here. And so I went out and set out to apply this to Angrites. Anyway, if you're interested in how you actually put trivalent chromium in olivine, there's actually a number of mechanisms. It's kind of unusual and odd. You wonder how you charge balance. There's a number of mechanisms that have been proposed to do this, and these are just these mechanisms. Probably the most dominant way is actually with a vacancy. So you can put a little trivalent chromium in olivine and charge balance it with an M site vacancy. You can also put it in as the spinel type substitution or a charge couple with aluminum. These are probably not the case. And so anyway, there are ways you can put trivalent. So it's a little odd if you're sort of interested in crystal chemistry. Why can you put trivalent chromium into olivine so readily? Well, you can charge balance, and it turns out that like for crystal field splitting reasons, it really wants to be there. And so that's the reason sort of behind this equal partitioning behavior. Anyway, so that's the sort of crash course. So the basic idea is olivines grow from melts. They pick up and inherit chromium valence ratios from their parental liquids. And if you're clever and you work really hard, you can maybe measure those, and then you can sort of translate those into useful redox information, and you can use that to interpret the oxidation state of the melt from which these olivines grow. And so just a brief slide about this. So the way that you actually measure these is you can go to a synchrotron. And so all of the work that I'm going to talk about here, and I'll just briefly talk about this since this is sort of the crash course in olivine valence. We did the GSE CARS 13 IDE beamline, which is at the Advanced Photon Source outside of Chicago. Anyway, so the basic point is we can take our olivines in thin sections, we can take them to the synchrotron, and we can actually measure X-ray absorption spectra. And so this is just an example showing you essentially how the X-ray absorption spectra of chromium 2+ and chromium 3+ in some standards changes as a function, or the absorption spectra for chromium, the chromium K edge, actually changes as a function of the chromium valence state. And so essentially we can actually exploit the presence of this feature right here, this sort of shoulder peak, as a quantitative measure of the presence of divalent chromium. So this peak right here on the main edge here actually only shows up when you have divalent chromium. And so we can basically take and we can measure the intensity of this peak, and we can translate that into chromium valence information. And that's the sort of long and short of it. But so the interesting part of all of this is essentially chromium valence ratios in and of themselves tell you something, but they're not quantitatively linked to redox states. And so to do that, you actually have to sort of come up with a way to translate measured chromium valence ratios in olivines into actual oxidation states or actual FO2 values. And so to do this, essentially, I had my graduate student Lydia, as part of her master's thesis, went down to UNM and did a whole lot of experiments in the gas mixing laboratory there and grew lots of olivines at a range of redox conditions. And then we took those to the synchrotron and measured their valence ratios. And so this is just a picture of the lab here. And so I like to call this the Rosetta Stone for redox. And the reason I call it that is essentially the raw chromium valence data can only tell you something about oxidation states if you put them in their proper context. So essentially, in order to translate those valence ratios into FO2 values, you need to know how things like liquid composition and temperature and pressure all affect the chromium valence ratio of the liquid, and by extension, the chromium valence ratio in olivines. And so we can access the information, but essentially we have to translate it. And so to do that, we do these experiments. This is just a diagram of how the gas mixing furnace looks like. And so basically the idea is we can suspend a little droplet of liquid inside of this furnace. we can equilibrate that and at, you know, temperatures as high as 1500 degrees centigrade. We can cool that liquid, and we can grow olivine crystals from it. And then basically we can drop quench that into water, and then we can take that, mount it, polish it, analyze it with the electron microprobe, take it to the synchrotron, measure chromium valence like that. And so here's a picture of Lydia in the lab. And so this is actually what these experiments look like. So she's not trying to rob the place. This was actually during COVID when she was doing these experiments on a trip down to UNM. So this is actually what one of these little glass beads look like. And so basically we took synthetic Angrite powders or synthetic Angrite compositions made out of oxide powders. We put them on these little wire loops like this. And so this is 2 millimeters. So this is rhenium wire. So then we took them, put them in the furnace, and we melted them at controlled redox conditions, and then we cooled them and let them crystallize. And so this is just a reflected light image of what one of these experiments, once it's mounted and polished, looks like. So you can see we have these nice little euhedral olivine phenocrysts floating in a matrix of quenched melt or glass, and this is the rhenium wire. So this is actually what comes out on the backside. And so then from this, we can actually take these to the synchrotron and measure chromium valence. And so this is just a little bit of this data. And so this is actually, this is data from a series of experiments we had done on Angrite, on Angritic melts. And so what this is essentially showing you is the measured chromium 2+ to total chromium ratio in these olivines. And so actually these olivines right here in this backscattered electron image of one of these little glass beads. So we took these to the synchrotron and we measured chromium valence ratio in all these olivines. And here we plotted them as a function of FO2. And so you can see that actually, so this sigmoidal curve is actually a theoretical curve that describes the shape of this relationship. And so you can see our data falls nicely on this experimental curve. And so we can actually take our data, our chromium valence data, and we can actually extract thermodynamic information used to model chromium valence. So we can actually calculate the equilibrium constant right here in this expression. So we can fit a curve like this to our data, and we can extract the equilibrium constant of interest, and then we can use that to model chromium valence in the liquids of interest. And so that's the basic idea here. And so once you have a plot like this, you can actually take measured chromium, or once you know essentially how the equilibrium constant or the thermodynamic properties of the chromium valence ratio in the liquid, once you've understood those, you can take that and then you can actually model chromium valence ratio in a range of liquids, and you can extract quantitative information from measurements made on real Angrites, not just experiments. So you can sort of think of these as the roadmap to making interpretation or to extracting quantitative redox information from real Angrites. So this is sort of how it works. This is an experiment we did. This is an olivine growth. So you can see the nice little olivine phenocryst. This is about maybe a couple millimeters in diameter. So they're pretty small. And this is all the data. So actually this experiment is this right here. So what I didn't tell you, and it doesn't really matter, it turns out there's an anisotropy problem. And so if you want to measure chromium valence in olivine, it's a tricky problem. So synchrotron radiation is linearly polarized, and so if you remember optical mineralogy, when you use polarized light and you look at minerals in polarized light, sometimes they're pleochroic. They're also birefringent. But anyway, so it turns out that like the chromium K edge, or there's some pleochroism in the chromium K edge that's related to the orientation of the olivine. And so essentially all of these sort of light color data are unanisotropy corrected CR valence data, or chromium valence data from these Angrites. And so then these are actually the anisotropy corrected data right here. And so they actually fall nicely on this curve. That's why there's this spread, in case you wanted to know. Anyway, so moving on, we'll actually talk about real Angrites now, because these are what we're here to talk about, not just experiments and interesting lab things. So Lydia and I, back in 2022, took actually more than two, but these were the main Angrites we focused on. 2 Angrites to the synchrotron, and we actually made chromium valence measurements. And so this is a large sort of kind of skeletal olivine phenocryst from NWA 78. This should say 12, not 14. And so what I'm showing here is on this backscattered image of this phenocryst, we actually selected and targeted individual spots. So the beauty of XANES is it's sort of like the electron microprobe or the SIMS. It's a spatially resolved analytical technique. And so we actually went and we measured chromium valence ratios at each one of these points. So we actually measured them across the iron zoning present. And here's a clinopyroxene phenocryst that we'll talk about later. So these are just the crystallographic directions of the crystal, which actually matter for the anisotropy correction that I talked about. Anyway, so the point is we made a bunch of measurements from these 2 meteorites. And so here's all of the data, all of the chromium valence data that we collected from these two meteorites. So this is cast as total or chromium 2 plus to the total chromium. And so I guess I didn't point this out. The amounts of chromium that we're dealing with in these meteorites is vanishingly small. It's less than 1,000 ppm. So it's about 500 ppm total chromium in these olivines. So it's very low. And so you have to go to the synchrotron to measure these things. And so we're measuring a very minor abundant polyvalent, or a polyvalent element with a very small or minor abundance. And so here I've just plotted our raw chromium valence data. So these are corrected for the anisotropy effect as a function of the mole fraction of the forest array component of the olivine. And you actually see there's this nice linear trend where the most chromium 2 plus enriched olivines actually were the most forest-aritic. And so you can see there's kind of a nice linear trend here on the data, except for these couple outliers. I'm not quite sure what to make of those, but this actually reflects changes in temperature, which I'll talk about here in a minute. And so basically the idea is we think that this is actually a fractional crystallization or temperature trend in the data. And so these are high temperature early olivines that crystallized from a more primitive melt, and these are lower temperature. So these sort of represent like this point down here, 04-3, they would actually sort of represent these sort of points down here. So less forest-aritic olivines. So there's this interesting relationship between chromium valence and forest-aritic content in these olivines. So anyway, using all of what I've told you, basically we've reconstructed the redox history. So using these experiments, we constructed models of chromium valence in angritic melts. And so then we basically use those models then to translate the chromium valence data into real FO2 data for these Angrites. And so this data is actually the first data of its kind. And so there's been no redox estimates really made for these primitive Angrites. So there's really no data out there on them. And so what I've done here is I've actually translated the chromium valence redox data into actual FO2 values and plotted that as a function of olivine liquidus temperature or just temperature. And so on this diagram, essentially these are common redox buffers. So this is the iron wustite buffer. So lots of times petrologists or geochemists who talk about planetary materials will talk about oxygen fugacities relative to the iron wustite buffer. So delta IW is the notation that they use for that. And so just for another point of reference, and so this is the IW buffer, and so this is the nickel-nickel oxide buffer. And so actually I've sort of made this into a sort of pseudo-phase diagram here. And so what I plotted here is actually the carbonate graphite equilibrium for Angrites. And so if Angrites came from, or if Angrites were derived by carbonated melting, you have to have carbonate stable in the liquidus. And so it turns out that like carbonate is actually fairly sensitive to the oxidation state of the phase assemblage that it's stable in, or potentially stable in. And so essentially in this sort of orange shaded area, this is the area or sort of above this line. So this is the dolomite graphite diopside equilibrium. So if you had you know, the Angrite parent body mantle, because it probably contains clinopyroxene that has a component of diopside, or has a diopside component, essentially you can write an equation that looks like this, or a chemical equilibria, and we can actually model the stability curve that defines essentially where you have carbonate stable versus where that carbonate's actually reduced to graphite. And so that's up here. And so clearly these group 1 Angrites plot nowhere near the carbonate stability field. So unfortunately, the carbonate partial melting hypothesis is probably not viable. And we'll come back to this idea in a few minutes when I sort of wrap this part of the talk up and talk about why that might be or what that might mean. And so clearly the Angrites, these primitive Angrites, are way too reduced to have carbonate stable in their liquidus. So there's no way they could really be the product of carbonated melting scenarios. So that pretty much rules that out, although there's still some questions about that. So you can actually play with the position of this univariate curve a little bit by changing silica activity and changing the activity of diopside that you might think is in the Angrite parent body mantle, but it really doesn't move it by more than about a half log unit. So maybe this line's a little fuzzy, but the basic point is if you look at where the Angrites plot in oxidation space or in redox space, they plot about 3 log units below. So if there's carbon in the Angrite parent body, in the primitives, in the primitive or the source regions for these primitive Angrites, it's probably graphite. It's certainly not dolomite, and it's certainly not calcite or anything like that. Carbonates just aren't really stable here, so we can rule that out. And so it turns out that the nebular hypothesis, the last hypothesis, or the sort of unusual bulk composition hypothesis first proposed by John Lange, that I said was kind of intellectually unsatisfying, it turns out that that actually requires core formation to take place. So in order for that hypothesis to work, you actually have to have a fairly large core in the Angrite parent body. And so, it's been proposed that it does based on some isotopic measurements, but there's really very little evidence beyond that, that the APB had a core. And so I think one way you can actually directly evaluate that hypothesis is that if you have primitive Angrites that come from the interior or come from the partial melting of the Angrite parent body interior, they should carry reduced signatures that are consistent with core formation. And so it turns out that actually, if you look at these FO2 values in log FO2 space, these are actually fairly consistent with the values that have been proposed for core formation based on siderophile element modeling. So those range from about IW -1 to IW -0.5. And so we get values about IW -1 from the chromium valence data. And so that's actually consistent with the core formation. And so in the absence of other hypotheses, it looks like that for now, the nebular hypothesis is probably the way to go. It looks like that these two Angrites at least equilibrated with a reducing environment in the Angrite parent body interior. And it also turns out that we can look at this from another perspective. So these two Angrites also have these interesting metal droplets in the olivine. And so these are just a few images of these metal droplets. So these are from NWA 12774. They have these little spherical droplets of camosite, and in some cases, the camosite's actually rimmed by little sort of little rims of troilite. And you can actually see inside of this troilite, there's a little camosite that's crystallized from the troilite. So these are just some X-ray maps of these. These range from 10 to 50 microns. The camosite composition, so I've actually measured these, ranges from about Fe95 to Fe90. There's no cobalt. There's not really any other elements that are appreciably present in these alloys. So it turns out that these can actually tell you something also about the FO2. So if you assume that these are equilibrium phases, and so there's a big question at first whether they were equilibrium phases, like what are these little droplets? Are they even meaningful? Are they, who knows, right? And so you can actually calculate FO2 from another equilibrium. So the presence of olivine alloy and silicate liquid with a defined silica activity can actually be exploited to calculate FO2. So the fact that this phase assemblage is saturated in a metallic phase actually can tell us something about FO2. And so we can actually extract numbers here. And so I've actually done this thermodynamic analysis. And so these actually give you numbers of about delta IW minus 0.9. So this is really consistent with the chromium valence data. So these Angrites, these very primitive, unusual Angrites, were probably reduced. And so this actually brings up an interesting idea that I've sort of wondered about. Could Northwest Africa 12774 actually contain droplets of core forming alloy? So maybe these are droplets or remnants from core formation or inefficient core formation, or perhaps these are really early first generation melts prior to extensive melting and core segregation. And so they've trapped these small inclusions that didn't efficiently settle and sink to the core. I don't totally know, but basically the story is this phase assemblage in the Zanes data tells you the same thing. These are reduced, so they have to basically come from a stability field outside of the, or come from an FO2 outside of the carbonate stability field. The Angrite parent body, like these are consistent with the core, the FO2s are consistent with core formation models. So it's a good question. And so just quick little aside. So it's also interesting that like in the matrices of these two Angrites, you actually see extensive immiscible sulfide globules. And so I think that probably there's some sort of fractionation of an initial metal droplets at temperatures greater than 1450 C. So I think that, if you take a model, if you use this ternary iron nickel sulfur phase diagram, and if we assume an initial melt composition for these little metal droplets of something like 5 mole% sulfur, that pushes the liquidus temperature of these melt droplets to greater than 1450 C. So initially you start out down maybe somewhere in this field where you have camosite plus sulfide, and so there's these tie lines in this phase diagram. And so the first composition of the alloy that you'd crystallize would be something like Fe94 nickel 6. And then essentially as you continue to crystallize these metals, as the temperature in this magma goes down, essentially you generate you crystallize camosite, and then the residual liquid becomes more and more sulfur enriched. Eventually to the late stage where you have these camosite droplets that are rimmed by just a little bit of late stage sulfide. And so these look an awful lot like the textures that we see. And so that's sort of my interpretation of what these droplets are. And so the source of sulfide in these particular meteorites, and perhaps other angrites, so sulfide's really common in other angrites. So essentially maybe these are fractionated metals that contain small amounts of sulfur initially, and as you fractionally crystallize these metallic droplets, they actually become more and more sulfur enriched until you sort of come into this field over here where you have sulfide liquid plus sometimes camosite. Anyway, enough about those. So a few takeaway points before I finish up my talk with a little bit of new data. So the oxidation state of these primitive angrites is consistent with core formation, which means they're consistent with the nebular hypothesis, as unsatisfying as that might be. So angrites probably really do represent the melting of an unusual admixture of ordinary chondrite-like components, plus some high temperature condensates, and actually some mixing calculations by Francois Tissot show how you can do this pretty well. Just a question of whether it happened like that. But it's looking more and more like that's the only way you can really explain it that's left. So this actually brings up a couple of other questions. So if you know anything about angrites, not all angrites are as reduced as these two. So if you look at more evolved angrites, they often have more oxidized redox signatures. And so the question is like, well, if you have this initially reduced body, then there went core formation, how do you explain these later stage oxidized liquids? I don't have a good answer for that. I have some thoughts, but I don't totally know. The other question that comes up is the carbonate melting hypothesis wasn't just based on this like similarity or on the similarity between angrites and some carbonated partial melting products from Earth. There's actually been some documentation of carbonate globules in some group 2 angrites. So group 2 are these sort of more evolved oxidized angrites like Dormany. And so like the question is if angrites are really this reduced, how do you explain carbonate globules in the few angrites where they've been observed? I don't totally know. This is still an open question. Like if you can't have them in primitive angrites, why do you have them in late angrites? I don't know. Maybe this has something to do with late volatile delivery and oxidation. So I won't talk too much about that, but that's my guess. Anyway, so finally on to some new data. So the second big question about angrites is how big was the parent body and where is it? And so this has been some really recent work from the last six to 8 months that I've done developing a new geobarometer to actually constrain the size of the angrite parent body. And so I won't take credit for proposing that the angrite parent body was big. It's actually been proposed by a number of workers for a long time, even though it's not a very widely accepted, I think, premise yet. So it turns out back in 2006, there was actually in some metamorphic angrites, there's these corona textures. So these are anorthite, clinopyroxene, spinellus, and plectites. And so it was proposed that you can only make these at high pressure, like 6 to 8 kilobars. So this sort of got dismissed and laughed off. No one really took it seriously, but it was an interesting observation nonetheless. And so there's also been some recent experiments on multiple saturation points for angrites that suggest that group 2 angrites originated from multiply saturated magmas at greater than 6 kilobars. So this sort of is the newer sort of arguments for a large angrite parent body. So in order to generate high pressures like 6 kilobars, you have to have a fairly large parent body. It's also been argued based on some geochronology results from Ben Ryder-Stokes that essentially the angrite parent body had an extended thermal history of potentially 40 million years. So this also sort of qualitatively nibbles around the edges and suggests that if you have these protracted thermal histories, the body has to be fairly large in order to maintain heat for that long. And explain some of the really young ages in this angrite NWA 8535, which is a dunite. And so he suggested, well, it has to be a big body. So all of these sort of nibble around the edge. None of these are smoking guns. They all suggest, I mean, maybe this is a smoking gun, but there's been other interpretations of how you can actually get this. Whether this is a true metamorphic symplectite or not, it's unclear. But anyway, so this got me thinking. And so the question I really have been wondering about, and this actually informed a lot of the work that I just showed you, so this is a bit out of order, but is how large was the APB and where did it even end up? And so this is a tricky question to answer and a slippery question. So by and large, I would say the community still thinks the angrite parent body was small, perhaps like 4 Vesta. It's a small differentiated body, asteroidal sized, a big asteroid. But there's some emerging evidence that suggests it could be much bigger. And so I was really interested in like how you might be able to confirm this or think about it in a more quantitative way. And so one way you can do that is actually with these clinopyroxene phenocrysts in these two Angrites. So these two unusual Angrites that I did all Zane's work on, it turns out that they actually have an unusual phenocryst assemblage. And so the fact that you have olivine plus CPX on the liquidus set in a ground mass with anorthite, that itself is indicative of a high pressure origin. So typically in basaltic phase equilibria, at low pressures in Angrites, you actually get olivine plus anorthite on the liquidus as early phenocrysts. But if you increase the pressure, you can actually switch the positions of anorthite and clinopyroxene on the liquidus. And so the fact that you have these two phases coexisting suggests that this wasn't a low pressure crystallization scenario. And so I actually think these porphyritic textures are related to some sort of complex polybaric crystallization scenario. And so you can actually use the calcium Schermack content or the CATS content of these clinopyroxene phenocrysts. And I've been working on developing a new geobarometer that basically exploits, I think there's a slide out of order here. Yeah, okay, I'll come back to that one. Anyway, so the Angrites have these really unusual clinopyroxene phenocrysts. Here's a backscattered electron image of one of these. And so it turns out that if you actually look at their aluminum content and you plot the aluminum in the M1 site versus the aluminum in the tetrahedral site, the clinopyroxenes from these two Angrites plot in a completely different area than all of the other Angrites. So essentially they're really enriched in this aluminum in the M1 site. So they're really enriched in octahedral aluminum. And so it turns out that the presence of octahedral aluminum in clinopyroxenes is fairly pressure sensitive. And so you can write this little exchange vector. So two aluminums substituting for magnesium and silicon. And so this actually, like if you substitute magnesium and silicon in a diopside with two aluminums to make the calcium Schermack component that we're talking about, you actually get a fairly healthy reduction in the unit cell volume. And so this is actually, when you convert it to molar volume in thermodynamic terms, this is a huge change. This has a huge molar volume change. So something like 3.5 kilojoules per kilobar. So this actually makes a good geobarometer. And so just the fact that these plot up here and are enriched in this component is sort of indicative of high pressure already. So if you just look at the mole fraction of this component, it's something like 30 mole percent CATS. So if you know anything about clinopyroxenes, this is like massive, monstrous. These are the most CATS-enriched pyroxenes, outside of a few that have been a few in-member CATS that have been observed in CAIs. These are the most CATS-enriched igneous pyroxenes that I'm aware of. And so it's actually hard to make CATS-enriched pyroxenes at low pressure. And so this can be exploited through this geobarometer that we proposed. And so to do this, essentially, if you know the activity of the CATS component of a clinopyroxene, and we can model the activities or chemical potentials of silica and anorthite, the anorthite component of the liquid from which they grow, you can actually calculate pressure. This little expression here. So this is what I call the CATS liquid equilibrium, and it's a good geobarometer. So here's the volume change of this reaction. So if you know anything about geobarometers, this delta V, and so this is in joules per kilobar. This is massive. So 1.2 kilojoules per kilobar for this reaction. So it makes a really excellent geobarometer. And so to apply this to the Angrites, you actually have to do some thermodynamic modeling with melts, or the inky melts model. You have to be able to calculate mu CATS, and so you need a solution model for that. If you know anything about pyroxenes are complicated and the solution models are tricky because of order-disorder effects. We also need an equation of state to model this curve, and so for that we've used a Murnaghan equation of state with some data from Holland and Powell. And so then we basically formulated, so this is the idea behind that. And so actually, like, Francois Tissot did a bunch of experiments that he based his sort of like hypothesized large Angrite parent body on. And so he actually used those to actually test and calibrate the barometer. And so these are some of his phase equilibrium experiments. And so rather than doing them ourselves, we actually took data from him and we calibrated our barometer with him. And so here's the results. So we took his experiments that he ran at pressures all the way from atmospheric pressure to 13 kilobars. And we ran them through our geobarometer and calculated experimental pressures with those. And here I have a plot of the calculated pressure versus the experimental. You get this nice fit in this one-to-one line. The root mean square error here of these experiments is about 1.35 kilobars. So that's a pretty good fit. There's 9 experiments. So these are just pictures of his experiments that I took from his paper. So our geobarometer works pretty well on his experiments. So what happens when we apply them to Angrites? So essentially, we've sort of inferred the composition of this ground mass, calculated the relevant chemical potentials with melts, measured the composition of these clinopyroxenes, converted the mole fraction of cats into mu cats. And so here's the pressures that we get. So here's the pressures from the cat's liquid barometer plotted as a function of the magnesium number of the pyroxene. So you can see that the pressures basically aren't really, the calculated pressures for these aren't really a function of composition. But basically the mean pressure that we get is about 18.5 to 19 kilobars. So that's the arithmetic mean of this population. So that's quite a high pressure. So that suggests that essentially the phenocryst assemblage in this sort of porphyritic meteorite grew at depth, at high pressure. So this is the first sample that we've known that actually has this assemblage for Angrites. So this is really interesting. And so it turns out you can actually convert these into sort of minimum size estimates for the Angrite parent body. And so unfortunately, because we don't know the depth at which these crystallize, you can't unambiguously translate these pressure estimates or crystallization pressure estimates into potential radii for the Angrite parent body. But we can say if you have an Angrite parent body, and so we've actually done a number of calculations using the core mass fraction inferred from core formation models, the densities. And so I can tell you at a minimum that the Angrite parent body had to be at least 1,000 kilometers in radius in order to generate a core mantle boundary pressure of 18 kilobars. So this is the bare bones minimum of a body size that you'd have to have in order to generate the CPX. So I mean, it's unlikely that these phase assemblages came from the core mantle boundary or crystallized near the core mantle boundary. So this is the bare minimum. So I've just for kicks here. So I've calculated clinopyroxene crystallization depths for a number of scenarios. So if we assume that the APB had the radius of Mars, we can calculate the acceleration due to gravity based on the relative masses and densities of the core and bulk silicate part of the body. And so essentially this would suggest that these crystallized, if the body were Mars sized, you'd have crystallization depths of 150 kilometers. If it were moon sized, these phase assemblages would come from something like 300 kilometers. So whatever you want this to be, you have to come up with a good argument, or essentially you have to think about how plausible it is to basically erupt a porphyritic magma from these depths, and that sort of gives you constraints on what the size might be. But at minimum, it's got to be 1,000 kilometers. Anyway, so I'll just leave you with a few thoughts here. The only way you can explain these aluminum-enriched clinopyroxenes is with a high-pressure origin. You can play with the composition of the melt all you like. The angritic melts basically can't generate clinopyroxenes that look like the ones that are in these meteorites unless you have a high pressure scenario. So that basically rules that out. Minimum radius of 1,000 kilometers. So the Angrite parent body was probably big. The porphyritic textures probably indicate a polybaric crystallization history. So these are a complicated crystallization history. Maybe these are first generation partial melts from the APB that got erupted onto the surface. So a big question that always comes up is, well, how in the hell do you get these unshocked Angrites from such a big body? And I don't really have a good answer to that, but I know there's been like these sorts of hit and run style collisions that are low shock, where you have low velocity oblique collisions that disrupt bodies and break them up with minimal shock. Perhaps that's what destroyed the Angrite parent body. It's also been proposed that the Angrite parent body or parts of it reaccreted into the inner telluric planets, the Earth Moon system, maybe Venus. We don't know. So with that, I guess I'm out of time, and I'll just leave you with a few conclusions. I've already talked about most of these. Anyway, so with that, I'll take questions, I guess, that anyone has. I'm happy to stay on and ask and answer whatever questions you might have. Anyway, thank you.
Thank you so much, Aaron. And yeah, we'll go ahead and open the floor up to questions. I know we're a little pressed on time, so we'll probably keep it to maybe just 2 or 3 questions. So for those that are online, if you want, you can raise your hand, or you can go ahead and put something in the chat. And then for those here in person, I'll call them. Go ahead, Walter.
So this is Walter Kiefer from Lunar and Planetary Institute. Very interesting talk, and I'm not a petrologist. I can't address your data for high pressure, large body, but I'm going to wonder, where did it go? Invoking a hit and run collision to break it up isn't enough, because now instead of having one big body, you've got a bunch of small bodies. You've got to comprehensively get rid of all of that out of the asteroid belt. And it's just another piece to consider in this. That's not a disagreement with your petrologic conclusions, but it's another problem that needs to be solved.
Yeah, that's a tricky problem. You know, it's unclear, like it's been proposed that a lot of the Angrite parent body might have reaccreted into the intertelluric planets, whereas some pieces got ejected and somehow got implanted and ended up in the asteroid belt. And that's basically the pieces of Angrites that we have now originate in the asteroid belt, even though that's not where the parent, those are fragments of the original parent body that basically partially survived intact. And maybe these are on the order of kilometer sized, but it's a good question. And I don't really know, but it's interesting because if you look at these dynamical accretion simulations, like they suggest that there's 10 to 100 moon to Mars sized bodies in the inner solar system. And so I'm suggesting the APB might have been one of those, which is kind of interesting that we actually have a sample that actually is maybe from one of these. But yeah, that's a hard question. I don't have a good answer. And, that needs to be thought about for sure.
Well, I don't have a good answer either, but thank you.
Thank you, Walter.
I have a question.
Yeah, go ahead, Chip.
I was just waiting for everybody else to ask their questions. You kind of skirted this issue, Aaron, a little bit, and you said you thought you had some ideas about what you were seeing here, but the chromium data from the olivines do suggest a fairly reducing melt from which the olivines crystallized. But again, the ground mass in some of those samples have a magnetite component, and some of the small fine grains, chromites, spinels. How does that evolve from a reducing magma to a much more evolved later magma?
So I have a good answer for this, and I've thought about it a lot because this has bugged me for a long time. And this is actually true in some other Angrites as well. It's not just these two, but in some Angrites, there's some late stage ovospinel. It's really ovospinel magnetite binary spinel. But this has bugged me for a long time. And so one of the answers is that they're simply not that oxidized. It's a bit of a red herring, I think. So you can actually do some calculations, and at these really low silica activities for Angrites, you can actually expand the stability field of magnetite relative to olivine and liquid substantially. And so you can sort of subsidize a small magnetite component stability, even at conditions down around IW plus 0, plus a quarter log unit. You can actually stabilize the magnetite contents that you see in Angrites. And so some of it's a bit of a red herring, because if you automatically assume that means oxidized, well then sure, it's a bigger problem. But I don't know that it's that much more oxidized than the early phases. And so it's a tricky problem. But yeah, I mean, even at reducing conditions, the Angrites are so iron rich. There's probably a small component of ferric iron present in these liquids anyway. And so, it just takes a little bit of that. If you fractionate these, if the ground mass is basically a fractionated derivative of these primitive Angrites, which in these two it probably is. And there's been fractional crystallization simulations that show that you can make the composition of the ground mass in these Angrites from primitive Angrites. Then you could actually have a little bit of light oxidation just by auto-oxidation and crystallization. So I think it's a simple conclusion, and it's not very satisfying. And that juxtaposition isn't as bad as stark as it looks on the surface. If that answers the question.
All right. Well, thank you, Chip. We have time for one final question. If anybody in the audience wants to ask one more. Okay, well, if not, then Aaron, thank you so much one last time. And then one final announcement before we all head out. Please join us next week. We'll have Carolyn Crow from University of Colorado. She'll be talking to us about zircons and chronology with them. So for everyone, have a wonderful rest of your week. And we will see you next week, same bat time, same bat place.